Hi everyone. Today I'm going to explain to you the little bit of the hands-on, the coding practice for steganographies. Basically, I want you to look at this the code. Uh, this works for bitmap the images, and because we are using here is bitmap, and it can be written in PDF at the end. So we import pix and then pill usually to manipulate the images, and then operating system OS. And with this OS, we need to change the directory where you can keep this code, and if you want to save the output files in that directory, then you need to do this. And then we need to create an image in RGB, red, green, and blue formats, and 3 by 3. So total 9 pixels can be generated. For each pixel, so location starting from 0, 0, 0, 1, 0, 2, 0, and 0, 1, 1, 1, and 2, 1, 0, 2, 1, 2, and 2, 2. This covers 3 by 3. And for this each specific cell, we can color in RGB. So red in full, and green and blue none in this case. On the second pixel, no red, no blue, only green. And then third pixel, only in blue. This on the first upper row, top row. And then in the second row, then we have a little bit of less red and little less green, little less blue, and then even less and less and less for that. And we draw this bitmap on the canvas. So bring canvas.canvas, and on that canvas we want to insert a bitmap files. The size is to I think this is I do not know the unit of this two, but this is pretty good size that we can recognize. And then this is a comment. And then finally, we want to generate from this canvas. The bitmap was written on the canvas, but if we want to save it, then this canvas right now has only this method, write PDF files. So we change it to PDF files. So this image can be saved in a given 01.pdf. Right now, this is steganography, the folder. So when I run this, then we will have given 01 files. So I bring that up here, exact same ones. So if I run this, see here given 01.pdf. So if I open up this PDF files, it's like this. Okay, I want you to compare this with another very similar the image files that you may not be able to see the difference. I changed only, for example, some of these numbers, okay? So you can see this on the next slide here. I changed from 255 to 254, and then the second row from 200 to 201. So one decreased and one increased. And then finally, I changed only RGB blue code only. I increased by one. All other codes remains the same, and I want you to see the difference if we do this. So I'm going to run it. Then the file name is give steg01. So this given 01 is the first program. This is the program that we changed one bit slightly, okay? Later we will see which bit that we want to change it, but anyway, one bit slightly changed. See how they are alike, okay? So it'll be saved in another file stack. So knowing that and experiencing that one bit, particularly least significant bit, if that is changed, then and also the image is really big and very complicated images, then almost impossible to figure that out, right? So that way we can hide the text inside the images. So change of this should be from the text, okay? So I'm going to run this. Then I have here give steg01 PDF generated. Sorry. So it'll be like this. Okay. I don't think you can identify this, even if you are very right. It's almost impossible to do that. Okay. So knowing that, I'm going to let you see both of those. And in order to do that, what we want to do, the image from image or text, for example, from given text, then we need to change it to binary. That way we can hide whether we want to change it from 0 bit to 1 bit or 1 bit to 0 bit or remains the same. All depends on the binary code for the text that we want to hide. So this is the code that we need to do. Very simple, right? There's each and that given messages for each character, we change it to the binary code and return the binary code. That's what it is. So if we say M, then M can be converted to this. Okay, this is exactly that you can find it from the internet. If you type ASCII table, text and binary, all keywords to find out some of the tables from the internet, then you can see this. In reverse, binary code can be reformed in a text. So when we hide a text into a binary, then we need to render the image in binary, and also given text needs to be converted to binary, and then by comparing the least significant bit in the image, and then we can add the text binary code. And when we want to extract, then in the reverse way, we can take the least significant bits, which is a binary code, and then we can convert that to a text. Then that is the text that we want to hide and transfer to secretly and privately is almost impossible to recognize. Okay. So we want to start from the BMP files only, and then next week either I am going to give you to expand this to deal with any type of images. To do that, you have to include another module. Okay, that module, using the modules, the textbook expanded all the codes very, very extensively, and discussed about the steganographies. So either you can refer to, I let you refer to the textbooks, or I may give you one last lecture, maybe something intelligent or deep learning, coding, the coding for deep learning. The course title for this is Secure and Intelligent Programming. So we spend so far the secure programming, because secure programming is first of all very, very important, specifically to your major. So whether we want to go deeper to discuss about secure coding, well, at last I can give you some of the ideas of intelligent codings. So I'll decide that and I'll post it next week. But right now, for simple approach, so we deal with the BMP bitmap files, but it can, as I said, this can be extended to deal with any kinds, any formats of what is it? Any formats of images. Give me a second. So steganography is, for example, if you want to deal with any type of images, then you need to download the CV2. That is written in the page 109. So after 109, all the coding list needs the modules. You can download it from OpenCV-Python. So you can install it by using pip install OpenCV-Python, and then you need to import CV2. on page 110 and 11 shows all the methods that you want to use. Okay, so this is very, very useful, the modules that we can use for steganographies. Okay, so keep that in mind. We may go back to that OpenCV modules next week, or I can give you some insight of the intelligent coding. But anyway, BMP files. For these BMP files, we need to import the same way, and then ask user to enter BMP files and read it. So img is nothing but image from PIL. img.open and open that files. So this im is nothing but image itself, BMP image itself. So from that images, we can get the size. This is some of the member field information, size. Then this will returns width and height. Okay. And this is the size of given images. Now, we want to get the text. Okay. So we need to ask, enter the message to embed the words. So we can enter some words, then we can get this guy converted to text, converted the text into a binary code. So this, the variable msgb is a message in binary. Okay. And here im, that is the images. im, here im, variable im, that is image. So we want to hide message b into im. Oops. And for each, so we need to scan from the top of this image, and then from the beginning of the text, and then we can swap that. So we want to hear I think that is in the next page. Yeah, here. Yeah, we want to set for each bit. If that is RGB, then in this CV2, the module extract the color code from the red. So it's not RGB. It's supposed to be all. Oops, here. I think here. Yeah, from here. This is extracting. Let me see. Okay, from here. So first to replace the given the least significant bit with the bit that we read from the messages. So all bit is a message bit from message in binary, right? So message in binary is iterable, which means we can access from wherever the position. Then we can move by saying next. Then we can move forward. If we say back, then it can go in reverse way. That is iterable. So we can do next. So for each bit of the message in binary, that will replace the image code. That's what it is. So new, the least significant bit, that is new all. And New G is new significant bit for green code. B is a new significant bit for blue. And then we put that pixel, okay? Put the pixel, that is the function, on this I and J from the beginning of that image, upper left corner of the image, which is 0.0, 0, 0. From there, we replaced with the new RGB code. This new RGB code is the bit from the messages. So we save it. Once we save it, so we will practice this later, and then we can extract it. The way that we can extract, here the size, ST image is image that we opened, okay? Once that is saved, in the previous example, we save it. It says say steganoBMP file, that is the file name. The way that I said here somewhere, I asked the user to enter the file name that you want to do steganographies. Okay, so it has two files: input source file, and then output files, and then messages. Message can be a file, of course. You can extend it, and that output file can be entered here. And this is steganography files. So we open it. So we call that ST images, steganography images. That images size, height and the width and height. So we change I and J code, geographical code. So we get the pixels from each cell of that pixels from upper left corner, which is 0, 0. And we extract the last bit for each RGB code. And then we here we convert it to the text. That's what it is. To text, this is a function. So we call that to text. So we can scan through and yeah, here we already get the to text, right? Up to that hidden sizes, and then we continue to do that. Okay, and this shows you how it doesn't show to you, hey, this is a hidden text, rather than doing that, because when we get this, we do not know the size of the text size of a message that we hide, right? It is generated from my opponent, my partner, remotely. So we do not know what is the size of the message that he sent. But anyway, it is hidden in the message that I received, which is a steganographed messages. So I need to scan through. I can extract the list of significant bits and convert it back to the text. We can do, for example, 3 characters each. Okay, and so at some point, from some points, if it doesn't make sense, then it is not really the text that we want to expect. That's what I have here for loops. So if we will run it, okay, this is enter source BMP files. Okay, this is it. I think I want to close this BMP files, and then I have another BMP files. When I change this to kind, at the end I have, for example, Lena BMP files. This is this lady. Okay, I want to hide the text into these images, and we can compare, see how it looks like, right? So by running this code, so I want to execute it. Source files, that is Lena BMP. So I type here. And then enter the message you want to embed. So I can say Mercy Cyber, enter. And then enter the file name that you want to save. This is the output file. Then I would say Lena steganograph, stag, Lena stag .bmp. Let me see if it is written in BMP. steganoBMP, PMP. steganoBMP. Is it BMP files? Let's say BMP files. Try and hit enter. Okay, it's done. So, oh yeah, here, stag Lena.bmp, and one below, Lena stag.bmp. So I want to show this. This is a Lena stag.bmp. This is Lena BMP. Of course, almost impossible, right? The image size is big. My text is small. So somewhere here, images start from here, right? Somewhere here that is maybe changed, right? It's almost impossible. And then if we want to extract it, here this is extract. So I want to run that program, and it enter the stag files that I will enter this Lena stag.bmp here. So enter, and then the character, it's not 10 characters, it's 3 characters, because I changed it here, 3 characters, right? But message is not correct. But anyway, so first the 3 character is more, and then if we hit enter, then next CY and space 3 character, and if I hit enter, then CYB. If I hit enter, CYBE, maybe some other issues right here, and it goes. If I do this, then after this, these all codes are not, doesn't make sense, right? So I can stop it, hit 0, then it'll stop. So this is something that we did this, but right now I created another very useful files here, and this Lena.bmp, I changed it to a file, both returns binary files. So we will be able to see what binary code of these 2 files are modified, from here original to this stag files. That's what we want to see. So output is a lana binary.txt or lana stag underscore binary.txt. We compare these two text files from these BMP files. Okay, so if I run this, then we will have that files to be generated, right? So I'll run that. Hit enter. Enter name of the step. No, I don't want to do this. This should be here. If I hit enter, yeah, it is generated. So if I change it to order date modified, this lana stag underscore binary.txt generated, lana binary.txt generated, and one before we have stag, lana stag.bmp, and lana is given. Okay, so I want to take a look at this by lana binary. Open with text edits. So this is this is a stag. Oh, this is original. And if I want to open up this, then this is stag. So what I want you to compare, if you compare these two side by side, this is RGB code. RGB, RGB, RGB. So first pixel, second pixel, third pixel, pixel by pixel. So in the first pixel, see if there is anything changed. Then I think this second one changed to 1, and in the list significant bits, the last bit, single bits, 0 still same, and next one 0 to 1, 0 to 1, and then 0 to 0, and the next one is 0 to 1, 0 to 1, and so on and so forth. So if we collect only this, the last bit, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, that may be more a small m, I would say. How can we tell it? I will bring up, for example, here, ASCII character to binary table. So hit enter. Then I think, yeah, this is okay. So small m, that is 0, 1, 1, 0, 1, 1, 0, 1. MER, I put MERCY, right? And E means 0, 1, 1, 0, 0, 1, 0, 1. So we'll look at that only. This is, let's see. Okay, here. So here, 0, 1, 1, second row 0, 1, 1, and third row 0, 1. That is this 0, 1, 1, 0, 1, 1, 0, 1, followed by E echo. Then this would be 0, 1, 1, 0, 0, 1. So we stopped here, right? And 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. So up to this. So we, from these, the bytes of a binary, the image files contains 2 characters of the messages. 2 characters, therefore 2 characters means 8 bit times 2, so 16 bits, right? So 1, 2, 3, 3 for each row. So how many? Three for each row. So how many rows? 1, 2, 3, 4, 5 rows. So 3 times 5, 15. So one more. So here. So this much image byte contains 2 byte of messages. Okay, so this goes like that. I think this is what I want to share with you, and hopefully you can practice this and get some understand. We can extend this to not only BMP files, but any kinds of files. The idea remains the same. The algorithm remains the same. Only the CB2 provides you a lot efficient method that we want to use. Here the method that we get here is get pixel or put pixel, but CB2 provides you a lot more than that. I think this is it for today. All right. See you later.